In part 11 of this series, special techniques, that is to say special methods, were discussed for the decomposition of samples. Decomposition is more or less sample preparation. It is used to qualitatively separate elements from the samples, then have each element separated for quantitative analysis. Gravimetric analysis relies on the final measured or calculated weight of the elements of interest. It is the final determination which is used for statistical analysis. Gravimetric analysis is the oldest and is considered to be the most accurate method of analysis used. It is also the lengthiest and tedious method to perform. This presentation is the starting point in our discussion of quantitative analysis for elemental concentration determination. I am Rob Boyko, Boyko Mineral Exploration, and welcome back. There are basically 5 methods of gravimetric analysis, the first being the physical method. It is simply a separation of material by mechanical sieving. Placer gold is a good example, where miners or prospectors use screens to separate, that is, to concentrate the material. Now this method is discussed in my published series titled The Fine Art of Fire. This series discusses the aspects of fire assay, and therefore this method of assay and subsequent concentration determination calculations will not be part of the discussions. However, gravimetric by filtration is similar to the physical method. The difference here is that sieves are not used. Gravimetry and vacuum-assisted filtering is. The material can be solid, such as sand in a liquid medium, or precipitated compounds in a solution. Decanting is another method of separating the material from a liquefied medium. Simply put, just carefully pouring off the liquid, leaving the residual material behind. Thermogravimetry is simply a method of separating moisture from a sample by placing it into a drying oven to dehydrate any moisture content, or by heating a sample to vaporize any organic material. In other words, burn the unwanted material off, similar to roasting sulfides from ore material. Now, volumetric gravimetry is used for solubilized elements of interest. These are ions in solution, that is, dissolved material. The analysis relies on the chemical reaction with a reagent and the analyte concentration, determined by some form of indicator. This method is referred to as titration. Last is electrogravimetry. It is a form of electroplating. The use of electrical potential and current passing through an electrolyte causes a reduction of metal ions to precipitate at an electrically charged cathode. The precipitate, which is a purified metal, can then be separated and weighed for the determination of concentration. Gravimetric, thermogravimetry, volumetric, and electrogravimetry will all be discussed in this series of presentations, starting with discussions surrounding the precipitative methods of analysis. Precipitation methods will isolate any element of interest as a sparingly soluble precipitate. To put it simply, the form precipitate can be considered as a product that will not redissolve, although it does very, very slightly. The sample may be of a known composition. However, if it is not known, it can be converted to a known product by using a suitable treatment. This method is slower and more tedious than a volumetric method, which will be discussed later in a future presentation. On the other hand, this method can be very selective in regards to the analyte or formed product, that is, your precipitate. In turn, the mass of an ion of interest in a pure compound can be determined, after which the mass percent of the ion in a non-pure compound can be determined. This method is primarily used for the determination of ionic compounds, that is, metallic compounds. The choice of an organic or inorganic reagent used for the precipitative reaction will affect precipitation. The process will involve the formation, isolation, and the mass determination of your precipitate. As example, silver nitrate is used to precipitate halides, which are chlorine, bromine, and iodine. Barium chloride is used to precipitate sulfate ions, while tetraphenyl borate is used for the precipitation of phosphorus, ammonium, rubidium, and cesium ions. The reactions that take place are between the cations and anions, which are the positively charged metal ions, and the negatively charged nonmetallics, such as nitrates or sulfur. All of these reactions will produce salts in the form of a precipitated compound. The atomic bonding is therefore ionic or electrovalent. The method used for the precipitation is considered as an absolute method, as the analyte concentration can be directly measured without any form of calibration. In order to conduct a successful precipitative analysis, there are basically three requirements that must be met. The first is in regards to the reagents that will be used. The reagent must only react with the ion of interest. If this does not happen, then you may not get the desired precipitate. Others may form along with the one needed for the analysis. The second is that the precipitate must be of sufficient quantity, as well as in a suitable form for separation. That is, that it must be filterable. The material must be large enough in particle size to be filterable, and it must be a single produced compound that is pure in composition. Last is that the product must be fully precipitated, or greater than 99.9% precipitated out of the solution. The method or procedure is somewhat easy to conduct, but lengthy and tedious. First, the raw samples are weighed, then dried and weighed again. The difference in weight is the moisture content, or concentration. The sample is then prepared by fully dissolving the sample using the right solvents and the method of dissolvement. A precipitating reagent is added and slowly precipitated, that is, ripened. More on Oswald ripening later. The sample is then washed and decanted, or washed and filtered, then dried or ignited to a constant mass. Once cooled, usually in a desiccator, it is then weighed. The mass percent of the element of interest is then calculated from the sample's dry raw mass and the mass of the precipitate. In general, precipitative analysis is used to determine the true concentration of a standard reagent. The testing and calibration of instrumental equipment, as well as any other analysis that requires a high degree of accuracy and precision. To fully understand the principles behind precipitative gravimetric analysis, there are some terms and principles that need to be discussed. To start the discussion, I would like to do a bit of a recap, starting with the process. It begins with the weighing of the raw sample. The raw sample is dried and reweighed for moisture content, and the weights recorded including the moisture concentration. The sample is then dissolved into a solution containing all the ions within the solution. A reagent is added to precipitate the required compound. The product is then washed and separated. It is then ignited or dried and weighed once more. The recorded data is then used for the concentration calculations of the element of interest. For the product to be a pure compound, a cation or an anion must be found that will chemically react to form the insoluble compound, being the precipitate. It must also be able to be precipitated out of the solution by 99.9%. This is when that common ion solubility table that I have mentioned in a previous presentation comes into play. For example, a sodium nitrate standard solution will be used for the calibration of an intercoupled plasma mass spectrometer. This solution has been on the shelf for quite some time. Although it was stored correctly, its strength needs to be determined for it to be considered as a primary standard. More on primary standards later. In order to determine its concentration, the silver nitrate will need to be converted to silver chloride. Potassium chloride will be chosen as the reagent. Assume that the KCl is a primary standard of a known concentration. Now the ion solubility table will show that potassium is soluble in water. It also shows that all nitrates are soluble in water. However, silver is not soluble in the presence of chlorine. It is listed as having a low solubility factor and will precipitate out of solution as silver chloride. This leaves the potassium nitrate soluble as ions in the solution. The silver chloride, after fully precipitating, can then be filtered from the solution and weighed. Concentration can then be determined. The nitrate and the potassium would ionically combine to form a potassium nitrate solution. If allowed to evaporate and no contamination present in the solution, the residue would be a pure potassium nitrate solid, that is, a powder. In order to achieve a good analysis, your precipitate must have some very important characteristics. That is, its properties. It must be a sufficient quantity. The amount of precipitate that is collected must be enough to be able to be separated, but there must be enough to be able to weigh it. The precipitate must be crystalline as well. It must be a solid, not a sludge. The crystalline structure's particle size has to be a sufficient size. Otherwise, a compound may just pass right through a filter during the filter and washing process. It must not be able to redissolve. Its solubility factor must be very low, or you will end up with product loss, and your analysis will be skewed. The precipitate or product must be pure. If not, the contamination will change the atomic weight of the compound and your final calculations will not be accurate. The precipitate must be stable and not reactive during a drying or igniting process. It must be non-reactive to the atmosphere. The bottom line is that it must have a stoichiometric composition. That is, it must be a single pure compound, such as the silver chloride that is shown in red in the reaction equation, not a mixture of compounds. Prior to having any precipitation form that is evolved, a suitable counter-ion will have to be chosen. Now counter-ions are ions that have opposite ionic charges, as shown in the periodic table. Silver has a +1 charge, and chlorine has a -1 charge. In the previous example, silver nitrate was converted to silver chloride. In the example, the chosen counter-ion was chlorine, which combined with the silver in solution to precipitate as a non-soluble silver chloride. The compound used was potassium chloride. In order to achieve a total precipitative reaction, the ionic compound chosen, being the potassium chloride, had to be a sufficient concentration to create a supersaturated chloride solution. The formation of the precipitate is a two-step process, the first being the nucleation phase and the second, that is the post-nucleation phase, which is actually the particle growth phase of a precipitate formation. Before any precipitation can form, a supersaturated solution of the counter-ion must be prepared. The example with silver nitrate in solution, the counter-ion for the positive silver ion would be chlorine, which is negative. The nitrate is in solution along with the chlorine, both existing as atoms floating around in a solution of water. Now, solubility rules state that silver will precipitate, as it is not soluble in a solution containing chlorine. The addition of chlorine from the addition of potassium chloride will dissociate into separate ions. The solubility rules show that potassium is fully soluble in water. An excess of potassium nitrate dissociated gives an excess of the chlorine ions. The chlorine ion will combine with a silver ion, forming a single molecule of silver chloride. Although microscopic, it becomes a solid floating around in the solution. That molecule is referred to as the seed molecule, better known as the nuclei of a crystal. Now there will be many nuclei floating around. By a process of collision and ionic attraction, these nuclei will spontaneously start to grow. This growth is governed by the nature and purity of the precipitate. If the formation of the nuclei is too quick, an excess number of nuclei will be produced in a very short time, resulting in small crystal size and low purity. This diagram by NDPI is a good representation of crystal growth by diffusion. The molecular ions, being the single molecules or nuclei of a compound, will start to diffuse, or ionically, that is, electrochemically combine or come together to form a crystal. As the nuclei form in numbers, the diffusion is instantaneous, as the molecules start to bump into each other. Now that's the simplest way to describe it. The crystal growth will continue until all the positive ions are depleted by the excess number of counter-ions that are capable of being diffused into the crystal lattice. A minute number will not fuse due to the process of equilibrium, which will be discussed later in the series. A fast production creates excessive nuclei. Too many nuclei will form many smaller crystal structures. Smaller crystal structures may redissolve due to the larger surface area created when measured collectively. Smaller surface area provided by a larger crystal size promotes a better equilibrium condition for crystal growth. This inhibits contamination within the crystal lattice. The contaminants are more likely to be reabsorbed into the solution instead of being trapped in the forming crystal lattice. Particle size is the most important characteristic of a good precipitate. As mentioned, the larger the crystal, the smaller the surface area, and vice versa. The example on the right shows this principle. Having 8 smaller cubes, let's say crystals, each of which has a surface area per side of 3 by 3, there are 6 sides and 8 cubes. The total surface area, when combined as shown, has a value of 432. Now this could be centimeters, could be nanometers, whatever. Now if these 8 cubic crystals were combined into one large crystal, it would have 4 surface areas of 12 by 3 and 2 surface areas of 3 by 3. This equates to a total surface area value of 162. The large crystal has less surface area. Now diffusion of the ions or molecules can be affected by stirring the solution. The temperature, the nature of the ions in the solution, and the concentration will determine the size of the growing crystal or crystals. The deposition of the precipitate from the solution is affected by the crystal's growth and, if any, the contaminants that may be present, as well as concentration. The solution must be saturated with a common ion. However, if the common ion is oversaturating the solution, crystal growth will be excessive, and the solution will contain too many microcrystals and therefore loss of measurable analyte. Now Weinman came up with a ratio that shows that the ratio correlates the precipitate with concentration and solubility. In order to minimize the nuclei concentration and microcrystallization, Q must be minimized. However, the solubility must be maximized, but not excessively. This can be achieved by using diluted solutions. This decreases Q. By adding the precipitating reagent slowly while gently stirring will keep Q as low as possible, at the same time keeping the solution homogenized, that is, no concentration zones in the solution. The solution may be heated, which increases the solubility of the precipitate, which allows for the redissolvement and reprecipitation of the precipitate. The pH value of the solution may also be adjusted, but not too much, as loss is due to redissolvement, which may occur. If the procedure is carried out for quantitative analysis, a little excess of the precipitating agent is added, and a check for completeness is conducted. However, too much reagent may introduce contamination into the crystal. Colloids are unwanted items. These are particles of precipitate that are microscopic. They range in size from 1 nanometer to 100 nanometers. Ions are attracted to the surface of a growing crystal by ion charges. These charges are either positive or negative. This will either attract an ion or repel it. The process is referred to as the zeta potential. As shown, the absorption of the molecular ion happens within a region that is very close to the surface of the crystal. Beyond the slipping pane, away from the crystal, is a small region referred to as the diffusion region. This is where the ions are either repelled or attracted. The rest is the ions floating around in the bulk solution. When there are too many tiny crystals, that is colloids, they will form suspensoids or emulsoids. Suspensoids are hydrophobic, that is, they tend to repel water, and due to their size and density will mix and float in the solution. Many, when left standing, will settle out of the solution as a residue. Many will not. Emulsoids are hydrophilic, that is, they will absorb water. These will also mix with the solution, however. They tend to form into a sludge or emulsion. These materials are referred to as gels. These tiny colloids may undergo a process known as flocculation. That is, they will have the tendency to cluster together. As for a solution filled with colloidal material, coagulation is the term used for the process of a liquid turning to a solid or semi-solid. The point here is that either these small crystals will pass right through a filter medium, and some being redissolved, or that the material will just plug up the holes in the pores in the filter medium, which forms a plug or clog, preventing separation of the analyte and therefore loss. By heating the solution gently while stirring, allows the minute crystals to redissolve and reprecipitate to form larger crystals. This is known as Oswald ripening, commonly referred to as just aging. There are other methods used to avoid a coagulated solution, and that is to add an electrolyte or a small amount of gelatin. Gently heating while stirring and a slow addition of the precipitating reagent appears to be best in avoiding a colloidal solution for most compounds. Interferences are basically contaminants, but they can also be two distinct compounds precipitating at the same time. Anderite is an example. In geology textbooks, its chemical formula, as shown, contains lead, silver, antimony, and sulfur. However, examining the ore, one could also see some silica, probably quartzite or quartz, and more. After pulverizing to -200 mesh, the sulfur is roasted off and the silica removed by the use of hydrofluoric acid. After the hydrofluoric acid is removed by evaporation with nitric acid, and additional nitric acid added for solubility, hopefully all that's left is nitrates of silver, lead, and antimony in solution. Now, potassium chloride may then be added to precipitate the silver in accordance to the solubility rules. However, the remaining lead will also precipitate out of solution. The results will be two compounds, silver chloride and lead chloride. The result of this co-precipitation is that the lead will need to be removed for a good analysis of the silver concentration. Most interferences are co-precipitants. Inclusion is another form of co-precipitation. Example: phosphates can be removed from mine wastewater by the inclusion of an excess amount of ammonium in the form of ammonium hydroxide, and magnesium in the form of magnesium nitrate. Now, both are soluble in water. When both of these reagents are added in excess, and the hydroxide moves the solution from an acidic state to a basic state at around pH 7.5, the ammonium magnesium phosphate starts to crystallize and drop out of solution. Now, if there were other ions in the solution that had the same ion charge, and roughly the same size. During crystallization, the ammonium ion may be exchanged with something like a potassium ion. Both of these ions have the same ionic charge, as well as they both are fairly equal in ionic size. However, both have different weights. The heavier ion can easily fit into the crystal lattice. The potassium molecule will be heavier than the ammonium compound. We can calculate the moles of ammonium magnesium phosphate, and from that figure we can calculate the concentration of the phosphate in the sample. So how do we know if there are any inclusions? We don't. All we have is the weight of the precipitate. This would make our analysis slightly skewed if potassium was in the solution. We would never know the concentration of the included ion, or what the ion is without instrumental analysis. Occlusions are similar to inclusions. The difference is this happens during a rapid formation of precipitate. Ions are not exchanged, but are trapped in the matrix. These ions can be water molecules, other analyte ions, reactive reagents, and others. These are counter ions. They are either negative ions or positive. The illustration shows that a bromine atom, being negatively charged, becomes trapped in the matrix of a silver chloride crystal. This type of contamination can be avoided by a slow addition of the precipitating agent. If contamination of this type is present, redissolvement and reprecipitation will have to be carried out. Now, if a precipitate is left standing for a longer period of time before filtration and washing, unwanted ions may be electrostatically attracted to the surface of a crystal and absorbed on the surface as shown in this simple diagram. This can be minimized by filtering and washing as soon as all precipitate is formed. Digestion with distilled water may also remove any soluble ions that become stuck to the crystal surface, followed with decanting and further washing. But if the contamination is severe, then dissolvement and reprecipitation of the precipitate itself may be necessary. Mixed crystal formation. Now this can be a real problem. The easiest way to show this is by displaying a magnified crystal. The crystal structure is isomorphous. That is, two or more species will have similar chemical formulas, such as barium-2 sulfide and lead-2 sulfide. They must also have the same geometric shape, that is, structure. During crystal growth, both species will form simultaneously and will entrap each other during the solid crystal formation. The result is two separate species locked together in a single crystal formation. If this type of interference appears, then the precipitate will have to be dissolved and the species chemically separated before reprecipitation can be achieved for each species separately. Mechanical entrapment of a contaminant can happen. This occurs during a rapid crystal formation. A minute amount of solution may become trapped in the fast-growing crystal as it surrounds a small amount of fluid, thus encapsulating it. The microscopic view of a contaminant shown in the picture on the right clearly shows this type of entrapment. The only way to eliminate the contaminant is by dissolving the precipitate and reprecipitating the element of interest. The new solution containing the ions will have less contaminant than the original, providing a lesser chance of recontamination. There are considerations. Some have already been mentioned. First is co-precipitation. Now this can be avoided by using diluted solutions to slow the formation of nuclei. A rapid filtration can be used to avoid absorption of contaminants. or unwanted ions can be removed by separation and/or using a masking agent. Now, if a precipitate is allowed to stand in a solution for too long, the introduction of a contaminant will result. To avoid post-contamination, the precipitate should be washed and filtered as soon as precipitation is complete. Do not let it stand. Due to equilibrium, which will be discussed in a future presentation, as an example, if present, zinc sulfide will precipitate out of a solution and then be absorbed onto the surface of a copper sulfide precipitate, or it will form with it as a post-co-precipitate. Now, peptidization is a process that affects colloids and gels. It is a process that disperses this material back into solution, which, in turn, will cause loss of analyte. In order to avoid this condition, an electrolyte is used. For example, diluted nitric acid is used to wash silver chloride, not hot water. The nitric acid is very diluted to avoid a redissolvement of the analyte. The common ion effect must also be considered. To obtain a good precipitate, a slight excess of precipitating reagent is used. Now, at first, the solubility of the analyte decreases, but then will increase. Adding too much of the common ion, that is, precipitating reagent, produces complex ions. For example, to precipitate silver, a chloride is introduced to form silver chloride, or that is a silver chloride precipitate. However, if too much chlorine is added, silver trichloride is formed. Now, silver trichloride is soluble in a chloride solution, resulting in the loss of the silver analyte. Now, the salt effect is another consideration. Excessive salts without a common ion present will decrease the number of ions that may precipitate. In other words, solubility increases and there will be less to no precipitate formation. This affects trivalent ions more than it does monovalent species. As already covered in this presentation, the right precipitating conditions can be achieved by using diluted solutions, heating the solutions, adding the precipitating reagents into the sample solution slowly while gently stirring, adding a slight excess of precipitating agent without oversaturating the sample solution with a common ion, using Oswald ripening, that is, aging, as well as controlling the pH balance of the sample solution. Now, filtering and washing is done as soon as possible after the completion of the precipitating reaction to avoid contamination. During washing, it is done gently, avoiding the use of excessive solution. This helps avoid partial redissolvement of the precipitate, thereby minimizing loss. For colloids, dilute nitric acid or acetic acid is used, or the use of ammonium nitrate can be added to avoid peptization of the precipitate. For filtering, a Gooch-type crucible or quantitative-grade ashless filter paper is used. As for drying and/or ignition, this is carried out to remove moisture and/or other unwanted volatile material. It must be understood that moisture may be reabsorbed into the sample from the surrounding atmosphere. Precipitating reagents may be hygroscopic, meaning that they have the tendency to absorb moisture. Drying is done by the use of drying ovens at temperatures between 103 and 110 degrees centigrade for an hour. They are then cooled in a desiccator to room temperature, and then the whole process is repeated for 30 minutes, reweighed and repeated until there is no significant difference in weight. Now, ignition is done in a muffle furnace or by a torch at temperatures that range anywhere from 600 to 1200 degrees centigrade. It must be noted that the carbon produced from the filter paper will act as a reducing agent and may reduce some compounds. Furthermore, moisture as well as carbon dioxide may be reabsorbed by the material during cooling. Therefore, cooling may have to be carried out in a muffle furnace or in open air to a temperature that is cool enough to be placed into a desiccator and further cooled to room temperature. Well, this concludes part 12 of this series on classical chemical assay. I introduce many aspects of precipitants leading into the topic of classical gravimetric analysis of your samples. I tried to discuss the topic in a way that would be understandable to any small-scale miner, prospector, or hobbyist that does not have a chemistry background. I hope that you found some benefit from this presentation, and I hope that it entices you to view part 13 of this series as I start the topic on calculating the results of any experiment on a sample that you may conduct. Now, if this presentation was of benefit, and you know of someone who would benefit from this presentation, please give it a like and a share. That's my only reward. I am Rob Boyko, Boyko Mineral Exploration, and I thank you for watching.